Okay, so we're going to start off Chapter 9, talking about sequences. So our first homework problem is problem number 5, and this first group says write the first 5 terms of the sequence given the equation. So number 5 is a sub n is the sine of n pi over 2, and so we always start at n equals 1, and then we increment it like this. So the first 5 terms, a sub 1 is going to be with 1 substituted, and a sub 2 is going to be with 2 substituted. And we'll simplify these in a second. We're just going to fill in for the first 5 numbers. Okay, so those we don't have change here. We can simplify that down to pi. That one's fine. Here we get the sine of 2 pi. And so we can put all our answers out here. These will be our first 5 terms. And from the unit circle, if we draw a unit circle, here's our x-axis. Here's our y-axis. And remember, the sine of theta equals the y value. So pi over 2, we get 1. At pi, y is equal to 0. At 3 pi over 2, it's negative 1. At 2 pi, it's back down to 0. And then 5 pi over 2 is the same as pi. So our first 5 terms, if we want to, do a sub n, this is the set of the numbers in the sequence. We'd have 1, 0, negative 1, 0, positive 1, and then dot, 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 dot. And that would continue on. The second problem we have is 8. So our equation for the terms in the sequence are negative 1 to the n plus 1 multiplied by 2 divided by n. Again, we're going to go through the numbers 1 through 5. This is the sequence with an infinite number of terms. So we're just going to do the first 5 terms. So again, a sub 1 is going to be negative 1 to the 1 plus 1 power times 2 divided by 1. The second term is negative 1 to the 2 plus 1 times 2 divided by 2. The third term is negative 1 to the 3 plus 1 power. And we set 2 divided by 3. A sub 4 is negative 1 to the 4 plus 1 times 2 divided by 4. And the fifth term is negative 1 to the 5 plus 1 power. And then we have 2 divided by 5. So when you have negative 1 to an even power, you get positive 1. So this will give you positive 1. And you see the pattern. This is going to be the odd exponent, so it'll be negative 1. This will be even exponent. So we're going to go plus, minus, plus, minus, plus, minus, and then we have the value. So we're going, this is plus, so we're going to have 2. Then we go to negative 1. Then we have positive 2/3, negative 1/2. I've simplified 2/4 into 1/2. And then this is to an even power, so it's positive, and so it's positive 5 2/5. So if I wanted to look at the set of numbers that are the terms in the sequence is going to be 2 comma negative 1, positive 2/3, negative 1/2, and positive 2/5. And then dot, 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 dot. That'll continue on as we increase n greater than 5. So the next group of problems is 15 through 20. So it's 6 problems, and what we're supposed to do is go to page 602 and try to match up the equations with the pictures. So let's just write down all the equations. And one thing you have to kind of think about is what is the behavior of these functions. The first thing you do is you look at the initial values. So when n equals 1, and then you can also look at how the behavior is as n gets large. You can also look at, is there an alternating sign? Does it go negative and then positive and then negative? And then after that, you might think about other things, but those are the so for example, this one right coming up here is just negative 1 to the n power. So when you have negative 1 to raise to some power n or n plus something, it's always going to bounce around between positive and negative values and so forth. Same with this one. So let's go ahead and do these first. Those should be the easy ones. So if you look at pictures C and D, you'll see both of those go plus or minus. They're positive one term, then they're negative the next term. D just goes between positive and negative 1. So this one obviously is D. And as a consequence, this must be C. And because these are the only two that have a negative 1 raised to some power. And this one, as you can see, as n gets bigger, this is going to become a smaller and smaller number. And so this should go up and down and then oscillate back, but then get closer and closer to 0 as you go along, which is that's what you see in C. Okay, so we've done that. Now let's look for ones. This one is n goes to infinity. This goes to 0 because you get 8 over infinity. So that goes to 0. This one actually, one of the things about limits of series is if you went and looked at the function, so instead of a sub n, if you looked at f of x is 8x over x plus 1, and you take the limit of this as n goes to x goes to infinity, you have this rational function where the highest order term is x to the first power, and you take the ratio of leading coefficients. So we know that the limit of this particular one as n goes to infinity of a sub n is going to be the number 8. So we would look on the graph and see if we see any that have a limit of 8, and the only one that has a limit of 8 is a. So this is going to be a. Okay. Now here we have something that is 0.5 raised to a larger and larger power. So this one's going to go to 0 as well. This one goes to 0. This one probably goes to 0 because factorials get very big. If you look at all the functions that are remaining, the only ones that are remaining are b, e, and f. They all approach 0 as n goes to infinity. So now, and you can also see that e and f start out at 4. So one of these doesn't equal 4 when n equals 1. Well, this one equals 4 when n equals 1 because you get 4 times 0.5 to the 0 power and any number to the 0 power is 1, so you get 4. So at n equals 1, this is 4, and at n equals 1, this is also 4. 4 to the first power is 4, and 1 factorial is 1. So both of these start at 4, whereas this one starts at 8 over 1. Actually, that one's also 4. So they don't start at 4, do they? Yeah, actually, they do all start at 4. Okay, so that didn't help any. One of these is going to get positive. It's going to be first get bigger and then smaller. So this one is always going to get smaller. It's always going to be decreasing, monotonically decreasing. This one, let's think about this one. So when we did n equals 1, we got 4 to the first power over 1 factorial, which is 4. Okay, let's do n equals 2. You get 4 squared divided by 2 factorial. So that's 2 factorial is 2 times 1, so that's 2. And so we get 16 over 2, which is 8. So this is the one that actually increases first, goes from 4 to 8. But then as you get larger and larger numbers, n factorial starts to become larger than this. And so this one, as a consequence of this initial behavior in the first 2 steps, is going to be B. Okay, so now we're back to, we only have 2 left. So this one's, I keep using the wrong color there. So this one is B. Okay, so these 2, one is E and one is F. So how do you find that out? Well, you could plug in n equals 2 into both of them. For n equals 1, we get 4. So n equals 2 here, we'll get 8 over 3, 8/3. And here, we'll get 4 to the 0.5 power. Well, that's a half raised to the first power, because n is 2. 2 minus 1 is 1. A half is 0.5. So you'll get 2. So this one's 2, this one's 8/3, which is greater than 2. So if you look at the 2 graphs, you'll see F has a value of a sub n, a sub 2 as being 8/3, and this one, number E, will have 2. So then we can make the final decision here. This is going to be F, and this one is going to be E. So there are the answers. So we didn't have to plot out the whole thing. We didn't have to calculate all the points. We looked at some general characteristics. First, we looked at ones that alternated. This one alternated between -1 and +1, so that one was easy. This one alternated positive and negative, but as n became larger, this fraction became smaller, so it kind of went like this, back and forth. So we got those 2. We had one case where you didn't start off with 4, so I just stuck in n equals 1 in here. And actually, I looked at this limit. All these 3 had limits of 0, or at least these 2 had limits of 0. This one's not quite so obvious, but it does as n goes to infinity. And then I ended up just plugging in one value to tell the difference between these 2. Okay, our next problem is 26. So these groups say, write the next 2 apparent terms of the sequence. Describe the pattern you use to find these terms. So here we have the terms written out. It's in your book. 7/2, 4, 9/2, 5. ... Okay, so what I see is it may not come directly to you, but what you would see is if I wrote all these with the same denominator, you can rewrite 4 as 8/2, 5 as 10/2. And then you should see an obvious pattern here. So they don't ask us to write an equation, but we're going to come up with one here. So what the first term is 7. So we'd have 6 plus n divided by 2. So when n is equal to 1, 6 plus 1 is 7. When n equals 2, you get 8. When n equals 3, you get 9. When n equals 4, you get 10. So that is the pattern that we're looking at. You had to rewrite the whole numbers as fractions to see it. I'm used to, when I teach math with liberal arts, I'm used to simplifying fractions a lot, so that kind of jumped right out at me. Okay, 31. Actually, let's do more than one of those. So let me write this down. So let's pick 30. So 30 is 1, negative 3/2, 9/4, negative 27/8. Okay, so one thing we see is this pattern of alternating. So that always means you've got negative 1 raised to some power. It starts out as even, so we're going to have n plus 1, so that when we start with n, we're going to have an even number. So when n equals 1, we get a squared, which gives positive. When n equals 2, you get a negative. Okay, the next thing is, I notice here I'm getting 2 to the first power, 2 to the second power, 2 to the third power. So I'm going to have 2 to the n minus 1 power. Because here I start off with 1, which is 1 over 1. So I got 1, 2, 4, 8. So 2 to the n minus 1, when n equals 1, you get 2 to the 0, which is 1. When n equals 2, you get 2 minus 1, which is 1. 2 to the first power is 2, and so on. Next time it would be 2 squared, 2 cubed. Now the numerator is a multiple of 3, so we're going to have 3 raised to the n minus 1 power again. Because here I have 3 to the 0 power is 1, any number to the 0 power. So 3 to the first power, 3 to the second power, 3 to the third power. Now, so that's the equation. But I could take this and combine them into one term because they have the same exponent. So I get 3/2 to the n minus 1. So here I'll have 3/2 to the 0, which is any number to the 0 is 1. And then when n equals 2, I get 3/2 to the first power, 3/2 to the second power, 3/2 to the third power. So that would be the next expression. Okay, we'll do one more in this set. So factorials are important. So finding the ratio, actually the next one's 31. If you ever take statistics or probability, which you have actually, most of you have had it, you end up with evaluating ratios of factorials. And remember, a factorial, let's say 7 factorial, is 7 times 6 times 5 times 4 times 3 times 2 times 1. Or it can be represented as 7 times 6 factorial, or 7 times 6 times 5 factorial, etc. You can group these two terms and rewrite them as factorial. So these 3 would be 3 factorial, these 4 would be 4 factorial, these 5 would be 5 factorial, etc. So what we do is to, instead of just multiplying this out in the calculator, is we can simplify it and make the numerator 10 times 9 times 8 factorial. We stop at the 8 factorial, because that's what I have in the denominator. So 8 factorial divided by 8 factorial, well, any number divided by itself is 1. So this just becomes 10 times 9, and so the answer is 90, which is a lot easier to multiply 10 times 9 than it is to multiply this all the way out 10 factorial is a pretty big number, and 8 factorial is the big number, not quite as big as 10 factorial. So that's the way you should do it anytime you see these ratios as factorials. Okay, our next problem is 34. So we're still talking about factorials. In this case, it involves the variable n. So actually, if you compare this to problem number 31, which we just did, if n equals 8, you'll get 10 factorial over 8 factorial. So what we can do is we can rewrite this as n plus 2 times n plus 1 times n factorial. And we divide by n factorial. So again, any number divided by itself, or any variable divided by itself, is 1. So we end up with n plus 2 times n plus 1. And we could multiply that out, n squared plus 3n plus 2 if we wanted to. So that's problem number 34. And I'm just looking at the other problems to see if there's anything that is worth doing. I think we're okay. Okay, 38 is the next one. Find the limit, if possible, of the sequence. So this is 38. Okay, so one way of doing this is if you have a function, and instead of substituting in, instead of using n, we use x, and then we take the limit of f of x as x approaches infinity. That limit will be the same as the limit of the sequence. And so what we can see is that the limit of 5 is just 5. And the limit of the second term is going to be 1 over infinity squared. So this term is 0. So the answer is 5. So the limit of this is 5. Therefore, the limit of 5 minus 1 over n squared as n goes to infinity is also equal to 5. Okay, 41, a sub n is equal to the sine of 1 over n. Again, let's take a function f of x, so we have the sine of 1 over x, and we want to take the limit as, so the limit of the sine of 1 over x as x goes to infinity is equal to the question mark. Well, if you think about what happens here, as x goes to infinity, you'll have this oscillating behavior, but this term gets smaller. So it's like the sine of 0, which would be 0. And so that's what my initial thought would be. As x goes to 0, this goes to infinity, so this thing actually goes near 0. It goes back and forth real quickly, and then as it goes out, it's going to get spread out. Let's just let's plot it just to make sure I'm thinking about that correctly. So let me share that with you. Okay, so what we're going to do is we're going to plot the sine of 1 over x. Now, as x goes to 0, then there is no limit, but as x goes to infinity, I think we should have something happen here. So yeah, here it is. So you can see as x goes to infinity, this is going to go to 0. If we zoom out, you can see that goes to 0, and if I zoom in the x direction, you can see it's going to approach 0. So I feel pretty confident that's true. So the same is true for the sequence. So the answer is going to be, for this one, is 0. And therefore the limit of the sequence as n goes to infinity is also equal to 0. Okay, we're still talking about convergence. We're going to do problem number 50. So the problem asks, determine the convergence and divergence of the sequence with the given nth term. If the sequence converges, find its limit. So our sequence is a sub n equals cube root of n divided by cube root of n plus 1. So the question is, does this converge or not? And one way to think about it is, I think what they're wanting to do here is use the squeeze theorem. So you can see if I take another function or another sequence, I guess they would call it another sequence, I think. Let's look at the squeeze theorem. So the squeeze theorem says if you have two functions that converge and your function is between those two functions, then your function is going to converge. So in this case, we really only need one other sequence, which is just actually, if I look at, if I remove the 1, so if I have the cube root of n cubed over the cube root of n cubed, that just ends up being 1. And so b sub n would just be 1. It would be a simple sequence. It would be 1, 1, 1, 1, 1, 1, 1. And this function, a sub n, this sequence, is always going to be less than b sub n. Why is that? Well, let's just look at an example. So if you get n equals 1, you'll get, we'll just evaluate, this is always 1, so we know that. If we can prove this is less than 1, then we're in good shape. Because the other function is 0. So that's why we only need to do one side. So what you get, if you get a sub 1, you're going to get cube root of 1, which is 1, divided by cube root of 1, which is 1, plus 1, and you get 1/2. Okay, so 1/2 is less than 1. If you do n equals 2, you get a sub 2 is equal to the cube root of 2 divided by the cube root of 2 plus 1. And that's going to be equal to something that's still less than 1. Let's just do it in our calculator. So 2 to the 1/3 power divided by 1 plus 2 to the 1/3 power is 0.557. 0.557. It's only 0.5. So you see it's getting bigger. But if n goes to infinity, what you'll end up with is this term will become insignificant relative to these two terms. So you'll just end up with the same number divided by itself, which is 1. So this a sub n is always less than b sub n. And since this converges, because it converges to the number 1, then this one converges. And as a consequence, that is actually what is, if you take the limit of a sub n, limit of a sub n as n goes to infinity, you're going to get, it's going to be equal to 1, because these two terms will become very large. If you had n to the millionth power, then the cube root of a million would be, what is the cube root of a million? I guess it's probably, I don't know, let's see what it is. So the million to the third power is 100. Okay, so you get 100 divided by 101, which is close to 1. And as this number, as n becomes even larger, it approaches 1. Okay, 63 is the next one. So we have a sub n is equal to 1 plus negative 1 to the n over n. So we also have this absolute value limit theorem. So let's write that down. What does it say? This is on page 598. So the limit, if the limit of n, as n goes to infinity, the absolute value of n equals 0, then the limit as n goes to infinity of a sub n also equals 0. So if we just do a few points here, let's say n equals 1. For n equals 1, you'll get 1 plus a negative 1 to the first power. So n equals 1 over 1, which is equal to 1 minus 1 over 1, which is 0. Okay, so that starts out as 0. Now if you do n equals 2, and actually what we're doing here is the absolute value. So it turns out it's still 0, the absolute value of 0 is 0. So that n, when you do n equals 2, you'll get 1 plus negative 1 to the second power divided by 1. And so that, in that case, you get 2 over 1, which is equal to 2. Okay. So let's say you take n equals 3, you get 1 plus negative 1 to the third power over, oh, I messed up over here. This should be 2 right here. So it's actually 1. So that's 1, 1, 2, again, 2, 2, 1. Okay. And then we have 3 here. So what do we get there? We'll get 0 over 3. That's the value. 0 over 3 is equal to 0. Okay, let's do one more. So that's the value 1 plus negative 1 to the fourth power divided by 4, which is going to be 2 over 4, which is going to be 1/2. So negative 1 to the fourth power is positive 1, 1 plus 1. So the numerator is either 0 or 2, and the denominator just keeps getting bigger. So what you can see is this number, in the actual sequence, it goes 0, positive 1, negative, actually 0, positive 1/2. So in reality, the absolute value doesn't make any sense. It doesn't really make any difference in this case. I didn't need to use that, but you can see that this does go to 0 as n goes to infinity. The denominator just keeps getting bigger, and the numerator varies between 0 and 2. And so since that doesn't grow, but the denominator does, then it goes to 0. Okay, we have another convergence question. 57. So a sub n is equal to 3 to the n over 4 to the n. And that is also equal to 3/4 to the n. So if you let n go to infinity, then what will happen is you have a fraction, number between 0 and 1, raised to some power n. And that is anytime you have a number between 0 and 1 and you raise it to a power, as the power gets greater, this number gets smaller and smaller and smaller, approaches 0. So let's just show you as an example, 4/3 to the 100th power. You can plug that into your calculator. So 3 divided by 3/4 to the 100th power is 3.2 times 10 to the minus 13th. Okay, so that would be one way of doing it, just knowing about fractions and raising them to large power. So the answer is going to be 0. I'm trying to think if there's any of these other this is an example of a monotonic function, meaning that if you plotted a sub n as a function of n, you start out at 3/4, so say it's 1. So you start here, and then it would get lower and lower and lower. It's always getting lower. Okay, so it is monotonic. And theorem 9.5 says if a sequence is bounded and monotonic, then it converges. So it is monotonic. Now, as far as bounded, bounded above says if there is a real number n such that a sub n is always less than m for all n. Okay, so that actually fits this bound. So our upper limit is 3/4, and any number raised 3/4 raised to any power greater than 1, integer power greater than 1, is going to be less. So our bounding, our upper bound is going to be 3/4. So it is bounded from above, and it's also bounded from below because it's never going to be a negative number. So it's going to be greater than 0 but less than 3/4. So based on that, because it's a bounded function, because it goes between 0 and 3/4, and it is monotonic, then it converges. As far as what it actually converges to, we just have to do what we did earlier. So the answer is 0. That's the limit as n goes to infinity for this particular function is 0. I was just thinking about if you had a function, would you be able to use anything we've learned up to this point? I don't think so. Okay, the next problem is 61. So we have that a sub n is equal to n minus 1 over n minus n over n minus 1 for n greater than or equals 2. So our sequence in this case starts at 2 and goes greater than that. So again, we can just try a few numbers, see what it looks like. So let's try n equals 2. So a sub 2 is 2 minus 1 over 2 minus 2 over 2 minus 1. And that's going to be 1/2 minus 2, which is negative 3/2. Okay, so we try n equals 3. A sub 3 is 3 minus 1 over 2 minus 2 over 3 minus 1. So I get 1. I get 2 over 2. 2 divided by 2 is 1. And the second term, I get 2 over 2, which is 1. So I get 0. Okay, let's try n equals 4. A 4 is going to be 4 minus 1 over 4 minus 4 over 4 minus 1. So that's 3/4 minus 4/3, which is, if we do it in terms of 12ths, we're going to have 9/12 minus 16 twelfths, which is negative 7 twelfths. So is 7 twelfths, that's smaller. Okay, let's do another one. So we get 5 minus 1 over 5 minus 5 over 5 minus 1. So we get 4/5 minus 5/4. So start to see a kind of a pattern here. 5/4 minus 4. Okay, so let's simplify it. And so in terms of 20ths, we're going to get 16 20ths minus 25 20ths, which is negative 9 20ths. And 9 20ths is going to be approaching, I'm trying to decide whether this, if we do a large number, let's try n equals 10, let's see what happens. So a sub 10 is 10 minus 1 over 10 minus 10 over 10 minus 1, which is 9/10 minus 10 ninths. Looks like it's approaching a half, I think. Is that right? Maybe not. Okay, let's do it again. So you get 81 90ths minus 100 90ths. So I'll multiply this by 9 and this by 10. And that leaves me with minus 19 90ths. Actually, it's getting smaller. So this number looks like it's getting smaller, and it's going to approach 0. There's no reason to believe that it's going to do anything other than that. So I would say the limit of this function as n approaches infinity of a sub n is equal to 0. Let's just try one really big number. That's not really big, but a sub 1,000. You get 1,000 minus 1 over 1,000 minus 1,000 divided by 1,000 minus 1. And so that's 999 thousandths minus 1,999. You see what happens. This is approaching 1 from the negative side. This is, from the lower side. This is approaching 1 from the upper side, and they're just going to get closer and closer and closer. So I don't even need to do that calculation. I can see that it does approach 0. So the answer is 0. Just want to see what I've only done one problem. I need to do another one. Yeah, let's do one more here while I'm recording this thing. 61. Okay, we got one more of these. Oh, I did that. That was what I just did. Okay, yeah, it was 61. So I actually did do 2 of them. So let me just stop there then. Okay, problems 73 and 76. These are the last 2 problems of assigning in this section. So what we're doing is we're trying to come up with the equation given the first 4 terms of a sequence. This one's pretty straightforward. So you can see we start at 2 and we just decrease by 1. We start at 3 and we decrease by 1. So the equation is going to be n plus 1 over n plus 2. And we start at n equals 1. We just go like that. So you can see when n equals 1, I'll get 2 over 2/3, then I'll get 3/4. Okay, so that was pretty easy. And then 76 is 1 plus 1/2, 1 plus 3/4, 1 plus 7/8, 1 plus 15/16, 1 plus 31/32. Okay, so obviously we're going to have 1 plus, and in the numerator we have 1, 3, 7, 15. So what I see there is 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1. So we're going to have 2 raised to the, well, here we have, when n equals 1, I want 2 to the first power. So that's good, 2 to the n. And then I subtract 1. So make sure that works here. So when n equals 1, I get 2 to the first power, which is 2 minus 1, which is 1. When n equals 2, I get 2 squared, which is 4. And then I subtract 1. And then the denominator is just going to be 2 to the n. So instead of, you'll notice each one of these, the numerator is 1 less than the denominator, and these are powers of 2. So there you go. That's it.